Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 10, 2026, just yesterday. It demonstrates that simulating future screens via renderable code allows a new model, Code2World, to rival GPT-5 in prediction accuracy and boost downstream agent performance by nearly 10% on the Android world benchmark. The paper is titled Code2World, AGU First World Model via Renderable Code Generation. And, as we'll see later, the implications for building reliable autonomous agents are quite significant. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core mechanism of this approach. On the left, we see the input, a current GUI screenshot and a specific user action, such as clicking a search button. Rather than trying to hallucinate the new image pixel by pixel, the central model generates the underlying HTML code for the next state. This code is then rendered to produce the final output on the right, which guarantees that the resulting interface is structurally valid and visually sharp. Well, Figure 2 details the system, split into data generation on the left and training on the right. The left panel shows the creation of the Android code dataset. It translates screenshots to code, renders them, and verifies the match using a metric called sig_lip. If the score is low, a feedback loop forces the model to revise the code. Moving to the right panel, the training advances from a supervised cold start to render-aware reinforcement learning. Here, the model produces multiple code samples and receives rewards based on whether the rendered result is visually and logically accurate. Alright, Figure 3 demonstrates how this model upgrades a standard GUI agent using a three-step pipeline called propose, simulate, select. First, in the propose phase on the left, the agent looks at the interaction history and suggests several candidate actions to achieve a goal, like moving a file. It assigns an initial confidence score to each plan based on its intuition. Next, in the simulate phase, Code2World predicts the outcome of each action. It generates the code for the future screen and renders it, showing exactly what the interface would look like. Finally, the select phase on the bottom right evaluates these simulated features. A scorer identifies which screen actually brings the agent closer to the goal, helping it choose the best action, even if the initial confidence was misleading. Table 1 summarizes the quantitative results comparing Code2World against various baselines. It lists the performance of pixel-based image generators at the top and versus LM-based code generators in the middle. The metrics are split between in-domain tasks on the left and out-of-distribution challenges on the right. Crucially, the bottom row shows that Code2World, despite being a compact 8 billion parameter model, achieves the highest functional logic scores. It hits roughly 94 on the SAD metric for in-domain tasks, narrowly beating even GPT-5. So, while the previous table focused on single-step prediction, Figure 5 evaluates performance in a live setting using the Android world benchmark. It compares the task success rates of 4 different agents, ranging from closed-source giants like GPT-4o to open-source models. The striped light blue bars represent the baseline agent, while the solid dark blue bars show the performance when augmented with Code2World. The gains are consistent across the board. For example, Gemini 2.5 Flash jumps from roughly 41% to 51% success. Similarly, the open-source Qwen3VL sees a relative improvement of over 22%, proving that the simulator effectively boosts real-world navigation. Well, while Figure 5 focused on the final agent, Table 3 performs an ablation study to verify which training components actually drive performance. The first row shows the base Qwen3VL model, starting with a functional logic score, SAD, of 59. The second row reveals that supervised fine-tuning alone provides a massive boost, raising that score to 78. Then, the middle rows highlight a trade-off, because using only the visual reward, RSEM, improves the rendering metrics on the right but stalls on logic, whereas the action reward, RACT, does the reverse. Finally, the bottom row confirms that combining both signals allows Code2World to peak at 94% accuracy. Wrapping up, 2 key takeaways stand out. Shifting from pixel generation to renderable code offers a far more precise way to simulate digital environments. And critically, this foresight capability, allowing agents to test actions in a virtual sandbox, seems to be the missing link for reliable autonomous navigation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.